Now that we can do proofs with sets, we could go back and take a look at all of the properties that we've used with sets so far, like De Morgan's laws, and we could actually prove those to be true in the same manner that we were doing proofs with sets before. I encourage you to take some time to go back and do that. In this video, what we're going to do is we're going to take a look at an example of a proof involving Cartesian product of sets. So I have sets A, B, and C, and I'm going to take a look at this equality of the Cartesian product of A with the union of B and C being equal to the Cartesian product of A and B union the Cartesian product of A and C. So this is a set proof, and it has an equal sign. So I'm going to break it up into two set inclusions. So the first one I'm going to look at is going to be that the Cartesian product of A with the union of B and C is a subset of the Cartesian product of B union the Cartesian product of C. So to do that, we're going to take an element, the ordered pair xy, in the Cartesian product of A with B union C. Now, elements in Cartesian product examples are going to be ordered pairs, so that's an important thing. And the first element in the ordered pair is going to come from the first set in the Cartesian product. So x will come from A, and y, the second one, will come from the second set in my Cartesian product. So y is coming from B union C. So then I think about what this means for x and y. Well, I can't really do a ton with x's in A, so I can take a look at y being an element in B union C, though. So y being an element in B union C means that y is in B or y is in C. Now, there's nothing different about B and C in this. I'm taking the union of the two of them, and all I know about them is that they're both sets. So I can, without loss of generality, say, let's say y is in B. Well then, the Cartesian product element, my xy pair, is actually an element in the Cartesian product AB. And that makes it that ordered pair xy is an element in the Cartesian product of A and B unioned with the Cartesian product of A and C, or really any other Cartesian product. So I have the inclusion that I was looking for, an element in the Cartesian product of A with B union C, and is an element that is in the Cartesian product of A and B unioned with the Cartesian product of B and C. So I have that subset shown. So now I have to show that the Cartesian product of A and B unioned with the Cartesian product of A and C is a subset of the Cartesian product of A with B union C. So let's take an element that's in the Cartesian product of A and B union the Cartesian product of A and C. So I'll have an xy element, and then I think about what this means. Well, this means that that pair, that ordered pair, xy, it had to have been an element in the Cartesian product of A and B, or in the Cartesian product of A and C. So again, there's no difference between these two. They both have A as the first set, and then whether it's B or C as the second set, there's no difference between those sets. So again, without loss of generality, I can just choose one and work through the proof from there. So I'm going to say the former, which means that xy is an element in the Cartesian product of A and B. Well, now that tells me that x is an element in A and y is an element in B. B is a subset of B union C, so that means that my ordered pair xy is actually an element in the Cartesian product of A with B union C. So now I have that subset proven. So now that I have the two subsets there's nothing that could be true about these except that they're equal. So I've now shown that the Cartesian product of A with B union C is equal to the Cartesian product of A and B union with the Cartesian product of A and C.